Now you may say DD is quite useful. However, on the negative side, DD does not provide any feedback to the user about its progress. Especially, you do not know whether DD is still running or it encounters an error. By default, DD will continue copy out data until the end of the file or drive, or until it encounters a bad sector or block on the source device that it cannot read. In the case of having a bad sector, it will just stop what it is doing. The user will have no idea of its progress and status. The option of CONV defines the conversion options for DD, since DD was originally designed for copy and conversion. Conv equal to no error sync is often used for forensic imaging to skip the unreadable sectors and continue copying. More specifically, conv equal to no error will instruct DD to pad the bad sectors with zeros and move on to continue copying the rest of the data. The sync option instructs DD to keep the sectors in the target device aligned with those from the source device. Thus, data will not be misplaced in the wrong physical location on the destination copy. Here is a one example of DD. You will see conv equal to no error sync will copy DD from /HDB to an output file called hdb.dd. If there is a bad sectors in HDB, DD will pad the bad sectors with zeros and continue copying. Remember that since DD is a simple tool for data duplication, it will not calculate the hash value for the newly generated image. Therefore, after the imaging process is complete, it is your responsibility to compute the hash values for both the original source and the DD image. Only if the hashes match, your forensic imaging process is done. When you present your case to court, you can prove that the image you used for analysis is the same as the original. If /dev/HDB has a bad sector and you use the conv equal to no error option, you have a complicated and interesting case. As you know, the hash value of hdb.dd will always be different from the hash value of /dev/HDB due to the padding of zeros. You have to document what has happened. This DD image may not be called admissible evidence depending on your action. Besides creating forensic imaging, DD has other uses. You may recall that in Unit 1, we emphasized that we have to sanitize the evidence drive before writing any data on the drive to avoid data corruption. You can use DD to wiping the drive with all zeros using this command. So in this case, input file is equal to /dev/0, and it will provide endless zero to the destination. This process will basically fill your target drive with zeros, overriding any data as it goes. Some sources said that very old hard drives might still contain residual data that an electron microscope might pick up after one pass of cleaning. Therefore, the Department of Defense standard for unclassified hard drive disposition requires 3 passes over every byte. Some researchers even suggest 7 passes of wiping. After wiping, you can reformat the drive. Now the drive is sanitized and ready to accept data. Now let's look at some examples of using DD for forensic imaging. In a drive-to-drive imaging, you physically remove the drive from the suspect computer and connect suspected drive to a forensics machine with a write blocker. Assume HDB is a clean wiped drive filled with all zeros, and HDB's capacity is larger than /dev/HDA. We can use both DD copies below to copy the content. What's the difference between these two commands? The differences are on the output file. In the first DD command, we copy every bit of HDA to a clean drive HDB. Since the size of HDB is larger than HDA, after DD is done, HDB will contain the data from the source followed by a bunch of zeros. Therefore, the hash value of HDB will not be the same as the hash of HDA due to these extra zeros. To obtain the same hash value, you can use DD to carve out the number of blocks copied from HDA, leaving out the zeros. Using the second command, since evidence.dd is a file containing exactly the data from HDA, assuming DD copied successfully, the hash value of HDA will be the same as the hash value of the file evidence.dd. If you choose not to remove a suspect machine for duplication, you can use a machine-to-machine drive image approach. In this case, we will simply connect the suspect machine with forensics workstation using a crossover cable or a FireWire cable. The forensic machine will listen on port 888 for receiving data. On the suspect machine, you are sending data and you run netcat. Now the input file certainly is from HDA and a pipe to netcat, the IP address of the forensics machine, and to the port 8888. And now here we use the option -W. It makes sure that the connection will be terminated after n of seconds, in this case 3, if the connection is not able to make or idle. After DD finishes, make sure the hash values of original drive and the DD image match. Before I finish talking about DD, I also want to briefly introduce DD's siblings, SDD and the DCFLDD. Both of them improved DD's functionalities by achieving better performance and also providing copy progresses. In a summary, this unit covers Linux Unix non-volatile and volatile data acquisition process and technologies. We will study Linux Unix file systems in the next unit, and I hope you enjoy the lesson.